Hello again, my dear students, and welcome back to the final part with this MOSFET lecture. In the previous part, we have investigated the MOSFET performance in terms of the metal oxide semiconductor junction, where we have discussed the three phases, including the accumulation, the depletion, and the inversion phase. And we see how we can estimate this V threshold or the threshold voltage using the metal oxide semiconductor energy band diagram. Now, in this final short part, we are going to discuss two interesting points. The first related to the charge accumulation inside the MOSFET, and the second related to the MOSFET capacity. So, first, what about the charge accumulation? As you can understand, the most important layer or part in the MOSFET is the channel layer, or this sub-layer just below the oxide film. Accordingly, we are somehow interested in investigating how charge varies under different biasing conditions for the gate, how charge will vary in this region. And actually, there is two ways where you can see how this charge varies, or what we call the charge variation in the channel. The first one, where you can find it in our lecture script, and maybe I also highlighted in the presentation, which is a mathematical modeling way. If you remember from our first lecture we have, or maybe from our materials course, we know that using the energy band diagram, you can calculate the potential phi, and that the electrical field is considered as the derivative of this potential, and the second derivative of the energy or of the electrical field, or the first derivative of the the second derivative of the energy or the potential, or the first derivative of the electrical field represents what's called the charge. So the first way is to do it mathematically. Starting from phi, which is the potential, you can calculate the electrical field, knowing that electrical field equals to d phi, negative d phi by dx, and then you can make it another round by making another differentiation for the electrical field to calculate what's called the rho, or the charge accumulation. Of course, I will not ask you to do this step by step. In case you need this equation, somehow I will give you directly in your formula sheet in the exam. But let's see how we can reach the same graph, but somehow using a very conceptual way instead of using mathematics. So what we are going to do now, my dear students, is that we have our MOSFET here, source, drain. This is oxide, and this is the metal, and this is the voltage applied to the gate VG. What we are searching for is, we are searching for the charge accumulation in this region under different biasing condition of the gate. Under different biasing condition of the gate. Okay, perfect. So let's make this VG, or the gate voltage, and this is Q, or the charge accumulation. Accordingly, we have here two cases. When VG is negative and when VG is positive. Of course, I have to mention that this is an N-channel MOSFET. Okay, so as this is an N-channel MOSFET, then you should insert what's called the positive voltage on the gate greater than what's called the V threshold in order to create this inverted N region. What if you insert a negative voltage? We already have focused on this in our previous part, if you remember. You can return it back if you forgot it. And we call, this is what's called the accumulation region. So whenever you insert here a negative voltage, which is this case in that second part of this graph, whenever you insert a negative voltage, what will happen is that this layer will turn to be more P. I mean, an accumulation of holes will start to accumulate on the surface. So we have some accumulation of holes. This is the case when the voltage is negative. Okay, then what about when the voltage is positive? Here, if you remember, we have two cases. We have the case where the voltage is still below V threshold, which what we call in the previous part the depletion region, or the depletion, sorry, not the depletion region, the depletion phase. In the depletion phase, the main target of this positive charge is to get rid of holes and to turn this layer from being a p-type to be intrinsic. So you can expect a very weak charge accumulation in this area. Then, once you reach a threshold voltage, this layer will turn to be an N-type, and we will enter what's called the inversion phase, where charge accumulation takes this manner. Of course, what you see on the right-hand side of this graph is electrons. Because herein, whenever you have a positive charge on the gate, what will be attracted is electron. However, when the voltage is negative on the gate, what will be attracted is holes. So this is the accumulation. This is the depletion. And this is the inversion. In some technical manner, maybe if you visit our reference solid state electronics bias treatment, you will know that there is two types of inversion, what's called the weak inversion and what's called the strong inversion. And this somehow appears on the graph. However, we will not go into such details. Maybe you can, maybe it be considered in other advanced courses like the BLSI or some postgraduate courses. But in this course, we will talk about inversion, depletion, and accumulation. So these are the main three regions of operation. And you can see this is the overall charge accumulation graph. This is a conceptual way. Of course, whenever it's conceptual, it will not be 100% clear why this function looks like this, and why this function looks like this, and why this function looks like this. Here we have to use mathematics. But in order to avoid long mathematical divisions, I just prefer to make it in a conceptual way to understand the concept. It's not so interesting for us to know the order of each function in these three regions. Maybe the overall trend is more interesting for us rather than a specific mathematical equation. So this is what's called the charge accumulation. Maybe I can invite you, my dear students, to do the same charge accumulation for a p-type channel, not an n-type channel. It will be somehow the same. However, there will be some difference in the biasing condition and the charge accumulation. Maybe this is somehow interesting for you to try to make it. Maybe we can consider it as a bonus question if you can make it and send it to me. Okay, that's perfect. So this, what's about the charge accumulation? Let me now return back to our PowerPoint slides. Yes, and this is a graph somehow, looks like what we have did. Here we have a full mathematical way in order to make this graph. Okay. Okay, now let's go to the second part of this lecture, which is the MOSFET. If you remember, my dear students, in chapter number 2 in the p-n junction, we have dealt with this parasitic capacitance associated with the p-n junction due to the depletion ratio, especially when your p-n junction is under reverse bias. Now, do we have an internal capacitance in the MOSFET? Let's see. What is the source of the internal capacitance? We have to first agree that our capacitance is usually have the same look, a dielectrical, an insulating layer in between two conducting / semiconducting material. So whenever you have a format in this manner, then you have a capacitance. And let's see, do we have such a format in our MOSFETs? Let's see. Okay, so first of all, before going into details, we have a very good sign that we have a capacitance, which is this dielectrical material. This dielectrical material is a perfect place where you can search for a capacitor, because basically this is a pure, an ideal insulator with a contact metal above and a semiconductor material on the bottom. So this, what we can call a gate capacitance. So the term gate capacitance, which is one of the most important parasitic capacitance associated to the MOSFET, is related simply to the existence of an oxide in the gate contact. Then, do we have more capacitance? The answer is simply yes. If you look here, my dear student, this is the source, which is an N type, and this is the body or the substrate, which is a P type. Accordingly, herein we have what's called a p-n junction. So a p-n junction, that means that you have a capacitor based on what we have learned in chapter number 2. Similarly speaking, on the right-hand side, you have an N-type drain region and you have a substrate, which is a p-type. Accordingly, you have a p-n junction. Then you have another capacitor. Herein, whenever you have a voltage on the gate, which is a positive voltage, greater than V threshold, then you turn this layer to be an N-type. And the body or the substrate is still a p-type. Accordingly, herein you have a p-n junction. You can find it, by the way, here. This is a p-n junction. This is an N region, and this is a P region. So simply, this is a p-n junction. So you have another source of capacitance. Generally, we have capacitance everywhere in a MOSFET, as you can see in this graph. Of course, I will not go into the mathematical details of the equations. I will just describe it as a concept. So here we have a drain body capacitance. Here we have a channel body capacitance. This is a gate capacitance. We have capacitance everywhere. Here we have the gate source capacitance. Yeah, you can see it here. This one, this is the source and type. This is the gate, and this is a dielectrical current. So there is a capacitance here, and there is a capacitance there. So all these are capacitance, and we can calculate them analytically or mathematically, as you can see in this equation. So you can have an equation per each capacitor. And then we can have this very famous capacitance model for a MOSFET. Maybe you will use it later on in your VLSI courses, or whenever you have to implement RF circuits or digital circuits where capacitance have a very important role in. So here, as you can see, we have this gate body capacitance, gate drain capacitance, drain body capacitance, gate source capacitance, and drain body and source body capacitance. So we have here five capacitance, which is, I think, similar to what we have here. Just here we combine both here in one capacitor, which is this one. So in this model, you have two connected capacitors here, and we have summed them in one capacitor here, as you can see. So this is a capacitor. That's why for every MOSFET, we have what's called the CV curve, or the variation of the capacitance, the variation of the capacitance with voltage, which is somehow similar to this whenever we study the accumulation of a charge with. Okay, so let's see how this capacitance vary. Let's see how this capacitance will affect our model. So in order to do so, let's go to here. Let's go to our whiteboard and start to plot the capacitance model. So this is the gate, this is the source, this is the drain, and this is the bottom. So as we said, we have a series of capacitors. So we have the gate body capacitance. We have the drain body capacitance. We have the source body capacitance, and we have the gate source capacitance and the gate drain capacitance, as you can see. So what we are intending to do now is to check the variation of these capacitance in terms of the gate voltage, VG. So we have these VG on the x-axis and the C, or the capacitance, which is the overall capacitance on the y. Okay, perfect. So first of all, in order to examine these capacitance, we have to check in each stage of operation which of these capacitance is dominating, which of these capacitance has a significant impact on the overall capacitance of the loop. So let me return back for a while to our presentation slide. Okay, so let me start with these p-n junction capacitors. So we have three p-n junction capacitors. The first one occurs between the source and the bottom. And the second one is between the source, so it's the drain and the bottom. And the third one is between the channel and the bottom. So for the first one, I would say that this is the most minor capacitor. Why? Because in most of the time, this source is grounded and the body is grounded. Accordingly, it's a thermodynamic equilibrium p-n junction. Of course, in a thermodynamic equilibrium p-n junction, you still have a capacitance because you have a depletion region, as we have studied together. But we can say that this is somehow not so critical. Why? Let's turn to the other side, which is the drain side capacitance. Here you have positive, N side drain and P-type substrate. The P-type is grounded and the N-type is connected to drain. In the N-type connected to the drain should be connected to a positive voltage in order to make current flow from the source to the drain. Accordingly, if you connect a positive voltage to the drain or to the N-type, that means that you turn this p-n junction to be a reverse bias p-n junction. Accordingly, in this case, the capacitance will increase due to the depletion region increase. As you know, my dear students, that the capacitance effect in the p-n junction is more and more significant whenever you have a reverse bias condition. So this reverse bias drain base capacitance will be more significant with respect to this source body capacitance. Okay, what about the third one, which is the channel body capacitance, which is actually hidden. You can find it here, what we call CD, or the depletion capacitance, but you will not find it here because it's somehow embedded when we combine these two resistors together. So this capacitance actually is very voltage dependent. Why? Because simply this capacitance, or what we call the depletion capacitance, occurs if and only if we have a voltage greater than V threshold. Because whenever you have a voltage greater than V threshold, then this capacitance starts to, then you have this N type layer, and then this PN junction starts to occur. However, if you apply a negative voltage here, that means that this substrate will be still a P type, which is the case, I think. Yes, here. So this is a P type. So there is no PN junction here. That's why there is no capacitance. Accordingly, this depletion capacitance, or the CCD, occurs if and only if you have a positive voltage on the gate. Otherwise, you don't have a CD. Then, what about the third capacitance? The third capacitance is simply due to the oxide thickness, which is a permanent capacitance is a MOSFET. So let's try to evaluate this on this curve. Here there is the accumulation region. Why this is an accumulation region? The capacitance is constant. Because simply in the accumulation region, the source and drain effect are neglected. So you don't have any important capacitance here. And the capacitance is mainly here. The capacitance is mainly due to this CG, the oxide capacitance. So this CG is the one which determines the impact of this capacitance. Now, once you go to the depletion region, then CD starts to appear. And as you know from your circuits course, whenever you have these two series capacitance, it's equivalent to the parallel of resistance. So whenever you have two series capacitance, its overall is smaller than the smallest one. That's why you can see that this curve starts to decrease herein due to the depletion capacitance, as you can see here. Okay, then after reaching the inversion, we have two cases, my dear students. The first case, when there is no voltage applied to the drain. So simply what will happen is this will continue, that the overall capacitance here is the depletion capacitance in parallel, or in series, I'm sorry, with the gate capacitance. But if you apply a positive voltage to the gate, then you have another capacitance in the game, which is the drain base capacitance due to the reverse bias. And now they are parallel capacitance. So the capacitance starts to increase again and reaches this value. Simply as if the drain capacitance compensates the effect of the depletion capacitance. Okay, let me make it one more round. So in the accumulation region, all these depletion capacitance have very minor impact. The only important capacitance, the only significant capacitance is the gate capacitance due to the oxide layer. So you have a constant somehow like that. So the capacitance you have is CG. Okay, then once the voltage turns to be positive, CD starts to appear. So now this becomes like this. This CG and this CD. This is the gate capacitance, and this is the depletion capacitance. Accordingly, the equivalent is CG plus CD over, or I'm saying CG times CD over CG plus CD. So that's why the resultant of this capacitance is smaller than the smallest one. Accordingly, you find this. Here, as far as you increase the voltage positive, you increase the voltage in the depletion region, this CD starts to increase, and accordingly, the overall capacitance starts to decrease. Okay, then what will happen? We have two cases. So in this case, we have two capacitance like this, CG and CD. Then what will happen after that? Still, we have another two cases. Either to continue like this in a saturation manner, I mean that the overall capacitance is CG and CD. Or to start to apply a voltage on the drain in order to conduct current, then your capacitance will increase again. Because now your capacitance equivalent will be CG, CD in parallel with CDP, or the drain-based capacitance. So this parallel equivalent will act to increase again the capacitance. So from this graph, you can study or you can investigate the difference of the CV curve by varying the gate voltage on your MOSFET device. As you can see, this is the accumulation region, this is the depletion region, and this is the inversion region. These are the three main regions of operation where you have different biasing conditions, either in terms that VDS is equals to 0, or you have a positive VDS. This is the case. So this is how we can demonstrate the capacitance inside the MOSFET in different regions, as you can see. And we consider this as the termination of our chapter number 4, dealing with MOSFET. The next chapter, my dear students, will be again with transistors, but in this time, we will go to a new or another bipolar transistor, which is a bipolar junction transistor. Please don't forget that MOSFETs are unipolar, however, BJTs are bipolar. So in the next chapter, inshallah, we are going to demonstrate together the PN junction, the PNP and NPN bipolar junction transistor. Thank you very much for your concentration. Hope that you have enjoyed chapter number 4 with MOSFETs. Again, this is the most important chapter in our course. Let's now return back to see you, inshallah, in next week with the BGT lecture. Thank you very much, and bye.